Have you ever typed a question into something like ChatGPT and gotten an answer that was so spot on, so human, that it felt a little bit like magic? Well, today, we're going to pull back the curtain. Because what's happening isn't magic at all. It's actually math. So let's dive in and break down how these amazing AI brains really think.
You ask a simple question, something like, "How are you?" And you get this back. It's polite, it's conversational, it feels real. And this is exactly what makes these tools so incredibly powerful. But it's also what makes them feel like such a mysterious black box.
So that's the big question, right? How does it actually do it? How does a bunch of code go from your few words to a perfectly constructed, totally new sentence? That is the mystery we're going to unravel today. Let's crack open that black box.
And the best place to start looking for answers is right there in the name of the most famous model of them all, GPT. We're going to break that acronym down, piece by piece, because it's basically the perfect roadmap for understanding what's going on under the hood.
Okay, first up, the G stands for generative. This is huge. It means the AI is creating brand new text, not just finding an answer on the web and copying it. Then we have P for pre-trained. Just imagine it's read a huge portion of the entire internet, plus a giant library of books. It's learned all the patterns of how we humans communicate. And finally, the T is for transformer. Now this is the real secret sauce. It's the special brain, the architecture, that allows it to truly get the context of what you're saying. So how does that transformer actually start processing your request? Well, here's the thing. A computer doesn't understand hello or how are you. It only gets one thing, numbers. So the very first thing that has to happen is translating our human language into something the machine can actually work with. And just look at this. A simple, friendly phrase like, "Hey there," gets turned into, well, a string of numbers. So how in the world does that happen? And more importantly, how does the AI hold on to the meaning of our words when all it's seeing are digits?
Well, it all begins with a process called tokenization. It's pretty straightforward, really. The model takes your sentence, chops it up into smaller bits, sometimes they're whole words, sometimes just pieces of words, and then it assigns each one a unique ID number from its enormous internal dictionary. For instance, if we take the quick brown fox, each of those words gets its own special number. The becomes 464, quick is 3863, and so on down the line. It's basically creating a secret numeric code for our entire language. But just having numbers isn't quite enough to really capture meaning.
See, just turning words into random numbers doesn't get us very far. The next step is where things get really fascinating. It's called vector embeddings. Each of those number tokens is transformed into a really long list of numbers, a vector. And this list doesn't just identify the word, it actually captures its meaning, its vibe, its essence.
A fantastic way to picture this is as a map of meaning. In this giant multidimensional space, words with similar meanings, like king and queen, are placed really close together, like neighbors. But here's the truly mind-blowing part. The relationship, the mathematical vector, from king to queen, is almost identical to the vector from man to woman. The AI is learning relationships through geometry. This is literally how it can understand an analogy.
Okay, so the model can turn our words into meaningful coordinates on a map. That's amazing. But human language is tricky, right? The very same word can mean totally different things depending on the words you put around it. So how does the model figure out context?
Well, first, there's a big problem with just turning words into numbers. You lose the order they came in. The model might not see the difference between dog bites man and man bites dog. Two sentences with the exact same words, but, wildly different meanings.
And the solution to this is actually pretty clever. It's called positional encoding. Basically, another layer of mathematical data gets added to each word's vector. This new information specifically tells the model, hey, this word was first, this one was second, and so on. This makes sure the original structure and meaning of your sentence are totally preserved. But what about words that have totally different meanings? This is where the real genius of that transformer architecture shines. Just look at these two sentences. The word bank is exactly the same, but the context, river in one, deposit in the other, changes its meaning completely. This tricky problem is solved by something called self-attention, and honestly, this is the core engine of the whole transformer. What it does is it lets every single word in your prompt look at every other word in that same prompt and decide for itself which ones are most important for figuring out its own true meaning.
So, in that first sentence, the attention mechanism lets the vector for bank pay really close attention to the vector for river. This connection essentially shifts its meaning towards the side of a river. But in the second sentence, it pays attention to words related to finance, shifting its meaning to a financial institution. It's dynamically building this rich, context-aware picture of what you're actually asking for.
Okay, so now the model has this deep, contextual understanding of what you typed. How does it turn all that understanding into an actual response? Well, the answer is surprisingly simple. It just predicts the next word, over and over and over again.
Here's how that works. The model looks at the whole context of your prompt, and it calculates the probabilities for what the single most likely next word should be. Then, and this is the really cool part, it takes that word it just predicted, adds it to the end of the sentence, and feeds that entire new sentence back into itself to predict the next word. It's this elegant loop, basically a super sophisticated autocomplete, building out a response one piece at a time.
You can see exactly what that looks like right here. If you type, "The capital of France is," the AI doesn't just know the answer in a human way, it runs the numbers. It calculates that the word Paris has a 95% probability of being the right next word, so it goes with the odds. And you know that temperature or creativity setting you might have seen in some AI tools? Well, all that's doing is messing with these probabilities. If you turn the temperature down low, it'll always pick the most likely word, giving you very predictable factual answers. But if you turn it up, you allow it to sometimes pick a less obvious word, which can lead to more creative and, sometimes more nonsensical results. All right, there's one last really crucial distinction we need to make. Everything we've talked about so far describes how a model works when you're using it, but that is very different from how it learns all this stuff in the first place. There are two totally separate phases. First, there's the training phase. This is an incredibly slow, super expensive process where the model gets built. It's shown billions of examples from the internet, and it constantly adjusts all its internal knobs and dials to get better and better at predicting the next word. Then there's the inference phase. This is what happens when you and I use it. All those knobs are frozen in place, it's fast, it's efficient, and it just uses all that prior training to generate answers without learning anything new.
So what this really means for you is that anytime you're chatting with an AI, you are always in that second phase, inference. You're not teaching it, you're not changing its fundamental knowledge, you're simply having a conversation with the finished product. And there you have it. We've gone from your simple words to number tokens to a massive map of meaning, all the way to a final answer that's built just one predicted word at a time. That's how these AIs really think. Which, of course, leaves us with a much bigger question. Now that we understand how they work, what should we be teaching them next? What do we want the next generation of these incredible tools to know? And that really is a conversation we all need to be a part of.